Hello, and welcome to this mini lecture on asymptotic analysis, as well as a walkthrough of question 1 on the worksheet. Asymptotic analysis is a method of describing the runtime of an algorithm with respect to the size of the input. When we're doing asymptotic analysis, we care about large input sizes. Why is this? Well, let's say that I have two different algorithms, and one has a growth function that's represented by y equals x, and the other has a growth function that's represented by y equals x squared. So you can imagine that the x-axis is input size, and the y-axis is runtime. When I zoom in to these functions when x values are small, I'm not seeing the full picture, right? And that's demonstrated by right over here on the graph on the very left. It seems like y equals x actually has a worse runtime, right? It seems slower. And it seems like y equals x squared is actually faster, right? It has smaller y values. It has a smaller runtime. However, as I proceed to zoom out and look at the bigger picture, I can see very, very easily and very clearly that it turns out y equals x has a much better runtime than the algorithm that has a growth function represented by y equals x squared. So there's two main reasons why we want to look at large input sizes. Number one is that small input sizes can be misleading, which is demonstrated very clearly by these graphs. And number two is the fact that algorithms are probably not going to perform that much differently in terms of runtimes if input size is 1, right? When it's really going to matter and when we're really going to see the impacts is when we have a lot of input to deal with, and there could be serious differences in runtime as a result of that, okay? So we are only doing asymptotic analysis on large input sizes. Now, let's talk about some of the key terms and key concepts that you need to know in order to do this, okay? So we're going to start off with big O. Big O is an upper bound on runtime in terms of input size. The runtime will never be slower than this bound, but the runtime is welcome to be faster than this bound. So if this was my growth function right here, my big O bound would be right here, okay? So that's an upper bound. Now, the complement to that would be big omega. Big omega is a lower bound on runtime in terms of input size. This is telling us that the runtime will never be faster than this bound, but the runtime can be slower than this bound, okay? So right here, this is my big omega, okay? It's a lower bound for my function right there, f of n, okay? Now, how about big theta? Big theta is a tight bound on runtime in terms of the input size. The runtime will always take exactly this much time. Now, big theta only exists when the tightest big O and the tightest big omega bound converge to the same value, okay? So we're seeing that right here, where this is our lower bound, and this is our upper bound, and they are converging to the same value. So we have a big theta. Okay, so this is a common source of confusion, but let's make sure that we make this distinction right now. So big O is not the same as a worst case bound, and big omega is not the same as a best case bound. Those things, those terms are not synonyms, okay? So what's the difference between them? Well, let's first figure out what is a case. So a case is a scenario where an algorithm receives a specific kind of input. Okay, so the best case, let's say that we had a sorting algorithm. The best case would be when I receive input that is sorted, right? I don't have to even do any sorting, right? I just maybe have to check and see, if it's already sorted, right? The worst case would be where I have, everything in like descending order or something, right? And so then I have to change the position of every single item in the list. Now, the point of this is that a case is defined by the type of input that's received, right? The structure, the contents, things like that, okay? Now, big O, big omega, and big theta These are tools that we use to describe the bounds of some function. It doesn't even have to be, a computer science function. It could be anything. It could be like, enrollment, like you see on Berkeley time, you see those graphs of like enrollment as like phases of, phase 1, phase 2, right? We could use big O, big omega, and big theta to describe the bounds of that function that we might see on Berkeley time, right? So that means that we can use, these bounds can be applied to any case, okay? Because the best case, the worst case, the average case, they're all going to have some growth function that we can put on a graph and then we can describe using O, omega, and theta, all right? So the best and the worst case, they are helpful when you're trying to find the tightest big O and the tightest big omega bounds for an algorithm, but that doesn't mean that they're exactly the same as big O and big omega, okay? In fact, best and worst case are bounded by big theta, because whenever I have a specific case where I'm receiving a specific type of input, I'm always going to end up with the same runtime, right? If I have, any input that constitutes like best, right? Anytime that I get an array that's already sorted and I put it into my sorting algorithm, it's always going to take me the same amount of time to deal with that type of input. And that's, like we discussed earlier, an instance in which we can use a theta bound. Okay. Now, that being said, you could still describe the best and the worst case with big O and big omega, but the most specific and informative way that we could discuss any case is theta. Okay, so I just threw this together really quickly just for you to quiz yourself. Classify each of these inputs as best case or worst case. Okay, now I'll go over the answer. So I'm sorry, the last two were kind of like trick questions. Okay, so the first is the best case, right? Because OSCE is the first item. And the second one is the worst case because OSCE is the last item. And these two down here, these are neither best case or worst case. Okay, why is that? Well, because the input size is 1, and we don't even have asymptotic analysis existing when n equals 1. That's small input size, and we don't do asymptotic analysis when input size is small. It's taken for granted, it's assumed that the input size is large when we're doing runtime analysis, okay? So it's another common misconception is to think that the best case is the case when n equals 1, right? So maybe you're asked for the best case runtime on an exam or something, and you look at the code and you calculate the best case as if it occurs when n equals 1. But that's not the correct way to do it. The correct way to do it, as we discussed earlier, is to consider the scenario in which an algorithm receives the best kind of input, the optimal input, okay? So cases are functions of input structure, input content, and not input size, because input size is always assumed to be large.